Hello everyone, and thank you for your time. Today I will be presenting some work that we have conducted on a small number of marked and recaptured otoliths from the tagging program. The presentation will be in two parts. One, the preparation and aging of those samples, and two, the OTC detection and analysis. For this study we had 40 yellowfin tuna otoliths and 38 bigeye tuna otoliths available for analysis. These ranged in length of recapture and also time at liberty. There was a small number of skipjack and little tunny otoliths that were provided, however the results today will only focus on the yellowfin and the bigeye. We have various sectioning planes of the otolith we can use. We have a transverse section, which is useful for daily aging and annual age, and a longitudinal section or a frontal section, which is well suited to daily aging. For this study, we chose transverse sections for two reasons. The first reason was that we wanted to be consistent with previous studies that have used daily aging on tropical tunas. And also we needed to be able to use those same preparations for annual aging, as has successfully been done in other tuna species around the world. We use a single section method where the otolith is embedded in a resin block, and one section, approximately 400 microns through the nucleus, is taken. Our first step is to prepare that for annual aging. So it's mounted on a slide and ground thinner to approximately 320 microns. And then it's imaged for annual age and then under UV for the OTC detection. The second step is to continue that preparation to allow for daily aging on that same section. For the annual aging, the methods we use follow those developed for other Pacific Ocean tunas that we've worked on, where we counted complete opaque zones. We assigned a marginal edge category based on the optical property of that edge, either opaque, narrow translucent or wide translucent. And then zone counts were converted to a decimal age using a nominated birth date of 1st July and the following algorithm. Now, I won't go into that algorithm just to save time, but I'm happy to talk about that with anyone later. So here we have an example of a yellowfin otolith prepared for annual aging, and we can quite clearly see the alternating opaque and translucent zones. As with other tuna species, we have studied the interpretation of the first three annuli, highlighted here by this red bracket. Is often difficult to interpret, but after this area the increment pattern becomes much clearer. And if we look at a bigeye otolith prepared for annual aging, we can see very similar otolith structure. And so this gives us confidence that the annual aging method is applicable for tropical tunas. We'll now move on to the daily aging methods. That same preparation used for annual aging was ground thinner and polished to allow for micro increments to be counted. The actual counts included a total count, a count from OTC to the edge, which we'll detail later, and where present, a count and measurement out to the 365th and the 730th increment. The techniques we used for the interpretation followed those we've used for other Pacific tunas. We can see the transect that we use starts at the nucleus and it works its way down close to the sulcus. At a count of approximately 150 zones, we follow a prominent check out to the outer edge and continue that transect down the outer edge. The transect's not always straight. You can see here in image B, our transect follows a path through the increments at their maximum concavity. And this just allows us to interpret the split and the merging zones better. We also do see within the otolith section these areas that do not seem to contain much increment structure or zone pattern. For these areas, we just use the pattern in the areas before and after, and then we estimate the number of zones that we think are contained within this area based on those two areas. So these methods are not dissimilar to methods used for other tropical tunas in the Indian Ocean and the Atlantic Ocean, with the obvious exception that these two studies started at the nucleus and counted out to the first inflection and then went down the outer edge. Those slight differences in methods shouldn't make any difference to the resultant age estimates. This slide shows you the micro-increment count of the daily age compared to length for both species, and we can see that the relationships are quite good. And the daily age is increasing with length as expected. When we compare the yellowfin work to another study in the Atlantic, the results are quite similar as well. When compared to bigeye and yellowfin estimated from daily aging in the Indian Ocean, we can see there are similarities in our estimates compared to estimates in the Sardin paper. However, when we compare the annual age to the daily age, we can see there's quite big differences in that the annual aging method is providing estimates of age far greater than from the daily aging method. For both species, we can see that divergence starts at approximately 1 year old. So this just reiterates the need for having marked, tagged and recaptured samples and running a program like the tropical tuna tagging program, and leads nicely into the second section, which is the OTC detection within the transverse sections. So our OTC methods for the annual preparation was to illuminate with transmitted light, and then an image was captured at 25 times magnification. The light source was then changed to UV to determine the presence or absence of the OTC mark, and an image was captured at that same magnification. This allowed us then to determine the relative position of the OTC mark within the transmitted image, so that we could count the number of opaque zones present between the OTC mark and the otolith margin. For the daily preparations, it was much easier. It was basically just a count of micro increments between the OTC mark and the edge. So here on the left hand side is an image of the microscope that we used for the OTC detection, and the right hand side is an image of a section under UV showing a clear OTC mark here. And it was encouraging to see for the majority of samples the OTC mark was relatively easy to detect. Now we need to be aware that just comparing the number of annual increments present after the OTC mark against the time at liberty can be misleading. This is because the count of annual increments do not provide a fractional age, and also largely the timing of the opaque and translucent zone formation is unknown in tropical tunas from the Atlantic. Therefore, we attempted to provide an estimated time at liberty, which is based on the assumption that the opaque and translucent zones are formed on an annual basis. It uses the position of the OTC mark relevant to the closest opaque zone, the number of complete opaque zones, and also the relative distance between the last opaque zone and the otolith edge, and we express that as a decimal age. So here we have a yellowfin tuna example of an annual preparation, and showing you the yellow arrow, which is the approximate position of the OTC mark, and the blue arrow is the first opaque zone, and the subsequent completed opaque zone is this cross here, and we have an edge. So we use these distances to approximate a time at liberty, and for this example we estimated the time at liberty at approximately 500 days, and that's compared to the true time at liberty of 575. So the comparison was quite good. This next slide presents the counts versus time at liberty for daily counts, for annual increment counts post OTC, and also the expected time at liberty based on the annual aging method. The blue line in each of these figures is a one-to-one line, and we can see that the annual aging method shows a much better relationship compared to time at liberty than the other two, and that the daily aging method seems to underestimate the time at liberty for nearly all samples. So even though there were differences between the daily count and the true time at liberty, it's also useful to look at where this divergence may occur and if there is some sort of fish size related pattern. Now these two figures seem to show that there is, and that divergence occurs at approximately 55 centimeters for both species. So this suggests that perhaps daily aging for the smaller samples is still a valid method, but as we move into larger length ranges, the divergence gets larger. So in conclusion, we can see that counting of micro increments in samples greater than 50 centimeters may lead to an underestimation in age. And however, daily aging for samples less than 50 centimeters still looks to be a valid method and is the best for determining juvenile growth. It's also extremely useful for verifying the age at which the first opaque zone is deposited, perhaps also out to the second. And the take-home message is that tropical tuna otoliths do contain annual growth zones, which have been validated in this study for yellowfin up to 159 centimeters and in bigeye up to 122 centimeters. So where to now? So we're hoping to publish this work. We'd like to add more samples to the analysis, which should extend size range and the times and liberties that we currently have. I'd also like to compare counts between transverse and frontal counts for both species on a small number of samples. And also we need to be aware that as time goes by, we need to recognise that there will be ongoing recaptures from this program, and valuable samples will still need to be analysed. So we need to keep the network open. I'll just leave you there with some relevant references, and thank you for your time.